So since most of you may not know me, so I thought of just starting off with giving a small introduction about our institute, the place where I work, and about our group. So the full form of ISER is Indian Institute of Science Education and Research, and this is an initiative of the government of India to promote research in basic science and education in basic science. So there are 5 of them in India, and one is in Pune. So geographically, Pune is about 150 kilometers southeast of Mumbai. And so coming to the type of work which I do, so I'm pretty new in the sense I've joined this place in 2010, and I'm trying to set up my group there. So we are interested in the area of computational material science. So what we want to do is to understand the chemical bonding and microscopic coupling in materials and use that understanding to obtain atomistic information of the electronic states, which are often difficult and sometimes even inaccessible from experiments. And also, this is a sort of an ambition to design new materials with the knowledge from the existing ones or to modify the existing materials. So mainly I'm interested in low-dimensional systems like clusters, nanovars, and surfaces. And one can calculate different properties. This list is not exhaustive. I've just jotted down some of them. And I use these properties to understand different processes, for example, in heterogeneous catalysis and new properties in reduced dimensions, nanoscale surface phenomena, long-range charge transfer excitation, and so on and so forth. And the tools which I use is the density functional theory, which is reasonably accurate and computationally affordable. And but it doesn't work for all types of systems, particularly for cases where the electron-electron correlations are important. So one needs to do some more approximations, and for the excited state properties, I use time-dependent density functional theory and constraint DFT. So all this is implemented in several open source softwares. This list is not exhaustive, and I typically use the Quantum Espresso. So okay, coming back to today's talk. So the talk is, sort of classified into 3 parts. So we'll start with looking into the interaction of graphene with nickel 111 and cobalt 0001 surface. While discussing this, I will also discuss about the difficulties one faces in theoretically modeling these systems within the density functional theory. And then we will I'll tell you some of the experiments we did in our computers on these systems. So we tried to functionalize this supported graphene with hydrogen, and also we looked into the effect of putting an oxygen spatial layer between the graphene and the metal substrate. So the first 2 parts are already published, and this is something which the we have just got the results, and we are doing the analysis. So so for graphene this audience doesn't need an introduction, but just for the sake of completeness, so graphene consists of sp2 hybridized carbon atoms with 2 sublattices, A and B, and all the interesting properties of graphene can be attributed to the presence of this Dirac cone, that is the linear dispersion of the electronic states at the K point of the Brillouin zone. So graphene on transition metals are interesting because of the different reasons. So for example, one can control the band gap of graphene by growing graphene on different substrates. These are also alternative routes for producing macroscopic graphene films on large scale. One can use these as catalysts to synthesize carbon nanotubes and nanofibers. And they have also been theoretically proposed as spin filtering devices. So a couple of years back, so in this Spearville paper, this group, so what they have shown is that they calculated the conductance of graphene layers sandwiched between 2 nickel electrodes, and what they find is that, so if one goes beyond 5 layers, one can attain 100% magnetoresistance in this device. So they looked into the current perpendicular to the geometry, and they rationalized it by saying that, so if one looks at the Fermi surfaces of this cobalt and nickel, so for the spin up channel at the K point of the Brillouin zone, so there is no Fermi, there are no electronic states present for the majority carriers in cobalt and nickel, while for the down channel there are electronic states present for the cobalt and nickel, and one finds also electronic states present in graphene, and as a result one can expect complete spin polarization. But the problem is the interaction of cobalt and nickel with graphene that alters the band structure of the graphene itself. And as a result, so the Dirac cone is broken, and it doesn't give you the perfect spin filtering. Also, so there has been a recent report that there has been induced, so experimentally people have observed induced magnetic moment in the graphene sheet, which is supported on nickel. So this is the XMCD spectra of the carbon KH, and one can see that there is a difference between the spectra obtained for spin up and spin down polarization. So however, this difference is pretty small, and it lies within the experimental error bars. So that's how we started looking into these systems. So we thought that first to look into the substrate, how the substrate interacts with the graphene sheet, and then to check whether actually there is in reality some magnetic moment. But while doing the calculations, very soon we realized that it's not a simple job, because so I'll come to the reasons later. So the first thing one noticed is that the graphene, the nickel 111 lattice parameter matches almost exactly with that of the graphene. And within the theoretical limits of the GGA or the LDA, so the GGA typically does a good job in describing the lattice parameters of both nickel and graphene. So whereas LDA, on the other hand, it tends to overbind the system. So from a theoretical point of view, one would prefer to use a GGA. But when we tried to calculate the potential energy surface of the graphene, of the interaction of the graphene sheet with the nickel, so these calculations are done in a configuration when the graphene, of the two inequivalent carbon atoms of graphene, one is on the top of the nickel and another is on the FCC side. And we vary the difference, the distance between the carbon and the nickel atom, and we calculate the binding energy of the graphene sheet per carbon atom. So experimentally, it's known that carbon binds on the top FCC site, but when we try to do the calculations within the limit of GGA, so we see that GGA hardly gives any binding. And the reason for this can be attributed to the following cause. So in these interactions between nickel and graphene, it's a subtle balance between the chemisorption and the physisorption. And in standard GGA functionals, the long-range van der Waals interactions are not included. That's the reason why GGA gives you, doesn't show any binding. So a solution to this has been proposed by Grimme quite some time back. So basically, he added a dispersive correction to the standard DFT energy functional. And if we use that dispersive correction, so now we see that, so this red one is for the potential energy surface with van der Waals correction. And if we zoom in to this region, so we see that we can correctly capture the two local minima. One is the chemisorption minima at around 2.1 angstrom, and another is the physisorption minima at around 2.85 angstrom. So in this point, I would also like to make a comment that LDA calculations in general gives you the shows that graphene binds, but that is more because of an accident rather than the accuracy in the calculations. Because inherently, LDA tends to overbind. So we then looked into the different configurations of nickel, of graphene or nickel and cobalt 001 surface. So we considered the top HCP, top FCC, and the FCC HCP. So, in the top FCC, basically one carbon atom is right on top of the topmost nickel, and the second one is in the HCP site. So in top FCC, similarly, one of the carbon atoms in the FCC sites, and in FCC HCP, so the two carbon atoms occupy the FCC and the HCP site. And from our calculations, we find that the top FCC is the most favorable, as it has been predicted by the experiments. And so the red ones, these are for on nickel, and the green one here, so the numbers below in the red parentheses, these are for cobalt. So we find that for cobalt, both the top FCC and the HCP FCC and the top HCP are equally probable to find. And this is also inconsistent with some STM measurements reported in the literature. So then we went on and tried to calculate the magnetization density. So basically these are isosurfaces of the difference between the spin up and spin down plotted in the real space. So the blue denotes, this blue isosurfaces denotes the spin down moments on each of the carbon atoms, and the red one denotes the spin up moment. So we find that in the graphene sheet, the magnetic moments on the two inequivalent carbon atoms, so they are ferrimagnetic in nature. So the top carbon atom is aligned anti-parallel with respect to that of the nickel atom, while the FCC carbon atom is aligned parallel with respect to the nickel substrate. And the net magnetic moment is about 0.01 Bohr magneton. And there is also a slight quenching in the magnetic moments of the surface nickel atoms. So in absence of graphene, the surface nickel atom has about 0.67 Bohr magneton magnetic moment. And if one takes the average magnetic moment of the graphene sheet, so it's aligned ferromagnetically or aligned parallelly with respect to the nickel. So in order to understand the origin of the magnetic moment, we looked into the band structure. So here I have just shown the contributions to the electronic states coming from the different carbon atoms in the graphene sheet. So basically 1 and 3 denotes the contributions coming from the top carbon atom, while 2 and 4 denotes the contribution coming from the FCC carbon atoms. So the first thing we notice is that the Dirac cone is destroyed, and there is an opening up of the band gap. So for the case of the top carbon atoms, we see that if the carbon atoms, the magnetic moment on the carbon atoms needs to be aligned ferromagnetically with respect to the nickel, then one needs to occupy this this anti-bonding type of orbital, which results from the hybridization of the carbon PZ and the nickel D. So as a result, this is energetically unfavorable, as it will cost energy in occupying these states. So as a result, for the top carbon atom, one sees the antiferromagnetic alignment of the spin with respect to the nickel substrate. While in the FCC carbon atoms, what happens is that since it occupies the hollow sites, so it's the PZ interacting with the DZX and DZY of the nickel states. So these states are much lower in energy compared to the nickel DZ squared states, and as a result, they are ferromagnetically aligned. So we also looked into the charge transfer. So basically, this is the difference between the charge densities on the combined system with respect to the individual components. So the blue isosurfaces shows region of charge depletion, while the red ones shows charge accumulation. So what we see that for the spin up electrons, so there is a transfer of charge from the nickel to the graphene sheet, while for the spin down electrons, there is a transfer of charge from the carbon atoms which are in the FCC site to the nickel atoms on the surface, And there is also some charge accumulation on the carbon atoms which are right on top of the nickel atoms. And as a result of this, if you sum them up together, so what we see is that on the top carbon atoms, there is a charge accumulation, while in the down carbon atoms, there is a charge depletion. So one can argue that the origin of the magnetic moment is also due to the difference between the different type of interactions for the spin up and spin down, which results in different amount of charge transfer. So for graphene on cobalt 001 surface also, we see similar results. However, I mean, since the magnetic moment on the cobalt atoms are much larger or compared to that of nickel, so the induced magnetic moment on the graphene sheet on the cobalt surface is larger compared to that of the nickel atoms. And as a result of which, the average magnetic moment induced in the graphene sheet is antiferromagnetically aligned with respect to the cobalt atoms. And also, similar to the nickel, we see there is a slight opening up of the band gap. So the summary of this part is that van der Waals interaction play an important role for the graphene metal interface, and in order to describe within the theoretical framework these systems, one needs to explicitly take into account the van der Waals interaction. So on clean graphene on nickel 111, it prefers the top FCC configuration, while on cobalt there is no clear preference. The spin moment of the top carbon atom is antiferromagnetically aligned with respect to the spin moment of the nickel cobalt systems. And for the FCC, it's a ferromagnetic alignment, and the average spin moment of clean graphene is ferromagnetically aligned with respect to that of the surface nickel layer, while it's antiferromagnetic with respect to the surface cobalt layer. So now if we revisit the charge transfer for the total charge transfer. So as I mentioned earlier, so there is an accumulation of extra electrons on the top carbon atoms, and there is a depletion of electrons in the FCC carbon atoms. So then we thought, what happens if we adsorb a donor or acceptor molecule on these surfaces? So we took the simplest one. It's a hydrogen atom. So it has one s electron which it can easily donate. So what we would expect is that the hydrogen atom binds to the FCC carbon atom, and so here I present the geometry of and also the magnetization density at a hydrogen coverage of half a monolayer. So this is the maximum coverage one can have when one tries to adsorb hydrogen. If you increase the coverage further, then the hydrogen dissolves, forming hydrogen molecule. And what we see is that the binding energy of this semi-hydrogenated graphene sheet, it's about minus 1.72 eV per 1/1 unit cell. And because of the strong binding of the hydrogen with respect to the FCC carbon atoms, so the magnetic moment on this FCC carbon atom is completely quenched. And as a result, we are only left with the magnetic moment on the top carbon atoms, which is aligned anti-parallel with respect to that of the nickel. So there is so the graphene sheet now becomes ferromagnetic, but the net alignment of the magnetic moment with the graphene sheet is anti-parallel. So then what we did is we changed the coverage of the hydrogen atoms. So this gives you the binding energy of the graphene as a function of hydrogen coverage on nickel. And we see that from the limit where there is no hydrogen to the saturation coverage, so the interaction between the hydrogenated graphene sheet and nickel goes from a weak chemisorption to a very strong chemisorption. And the magnetic moment also changes from a positive. So there is a change in the sign of the magnetic moment on the graphene sheet. So it changes from positive to negative. So basically what we've achieved is by quenching the magnetic moments on the FCC carbon atoms, by varying the hydrogen coverage, one can tune the net magnetic moment on the graphene sheet. So on cobalt also, we see similar features. So what we see is that because of the interaction with the hydrogen, there is a strong buckling in the in the geometry of the graphene sheet, and also there is a huge opening up of the band gap. However, in cobalt, if you look at the magnitude of the magnetic moment, so these are again much higher compared to that of the nickel atoms. So to summarize this part, so what you have seen that upon hydrogenation, the hydrogen atom binds to the charge deficient FCC carbon atoms. There is interaction between the graphene sheet changes from weak to strong chemisorption as one increases the hydrogen coverage. On nickel, we observe a spin reversal of the induced magnetic moment on the graphene sheet with increase in the hydrogen coverage. And in cobalt, there is a 6-fold increase in the induced magnetic moment on the graphene sheet. And additionally, there is a huge band gap opening at the K point of the Brillouin zone. So after this, we thought that, okay, I mean, let's see what happens if we put a oxygen spatial layer and in these systems. So, I mean, this was sort of motivated by the studies of these thiophelanins and porphyrins on substrate with an oxygen intermediate in between. So, so what we did is, we did both for the graphene sheet and also for the semi-hydrogenated graphene sheet. So we considered different possible configurations. So for example, the top FCC, top HCP, HCP FCC, so these I have defined already. So the bridge top and bridge HCP and bridge FCC, so the convention which we follow is that, so when I say, for example, it's a bridge top configuration, so what I mean is that, so with respect, so the two carbon atoms, so the top atom is the central site, the two carbon atoms is at the bridge site between the top and the FCC positions, and the bridge site between the top and the HCP position. And in all these cases, what we find is that the interaction between the between the graphene sheet and the substrate, it is mainly due to van der Waals interactions. And so the distance between the carbon atom and the nickel, between the carbon atoms of the graphene sheet and the oxygen surface, so that is about 2.85 angstrom. And if one, so this is the density of states for the, so the red and green one are for the nickel and the oxygen atoms, and the blue one and the, and okay, there is a black one also, but since they are same for the carbon one and carbon, for the two carbon atoms, so they are overlapping on each other. And if one looks at the band structure, so what one sees is that due to the interaction between the, because of the weak van der Waals interaction, the Dirac cone here in this case remains intact for both the spin up and spin down. Only there is a shift of the Dirac cone with respect to the Fermi energy. However, when we put our semi-hydrogenated graphene sheet on nickel, 111 covered with oxygen, so what we find is that the interaction is very strong. So the binding energy of the semi-hydrogenated graphene sheet is about minus 2.58 eV. Also, the carbon atoms which doesn't contain the hydrogen, so they form covalent bonds with the oxygen atoms. So as a result of which the magnetic moments on the graphene sheet is completely destroyed. And also, if one looks into the magnetic moments on the oxygen atom, so the ones in blue are in the limit when these two systems don't interact with each other. So there is a slight increase in the magnetic moment on the oxygen atoms, and the carbon atoms more or less are completely destroyed. But what is surprising is that when we look at the surface nickel atom, so there is a huge enhancement in the magnetic moment on the surface nickel atom. So in absence of the semi-hydrogenated graphene sheet, it was about 0.36 Bohr magneton. But while when we hydrogenate the graphene sheet, so it increases almost 3 times. So, I mean, this looked quite unusual and unexpected for us because, I mean, I don't know, but most cases when we see that we have a molecule binding to a magnetic substrate, it's usually the magnetic moment quenches. But here we see it the reverse direction. And so we looked into the charge transfer for this system. And so what we see is that there is a flow of, for the upspin cases, there is a flow of electrons from the the semi-hydrogenated graphene sheet to the nickel through the intermediated by the oxygen atoms here, while for the downspin, it's in the reverse way. And, and, in the total, so what one sees is that there is overall there is a charge deficiency in the semi-hydrogenated graphene sheet, and there is a charge accumulation in the nickel atoms. And so we try to rationalize this by by doing a band alignment of the systems when these two are not interacting. So for the nickel oxygen case, so this is the Fermi energy, and for the semi-hydrogenated graphene, so your HOMO is located here. So one can expect a flow of electrons for the upspin channel, flow of electrons from the semi-hydrogenated graphene sheet to the nickel substrate. But what is puzzling till now for us, and I mean, frankly speaking, I don't understand why. So if you consider the downspin channel, the carbon states are way down the below the Fermi energy here. So these black graphs is for the carbon atoms, and the nickel state, the states coming from nickel and oxygen, the ones in red and green. So at the Fermi energy, there are hardly any states. So I mean, if one think of a transfer of electrons, so one would have expected, one would have thought of transfer of electrons from this state to this state, which is about 4 eV in energy, the difference. So this is what is puzzling, that I mean, in the non-interacting limit, there is such a huge energy barrier one the electrons needs to have in order to get the charge transfer. So this is something which we still don't understand, and we are trying to rationalize it. So coming to the conclusions, so what we have seen that introduction of a spacer oxygen layer decouples the graphene sheet from the nickel substrate. For this case, the Dirac cone moves above the Fermi energy due to weak interactions, and hydrogenating the graphene sheet results in a strong interaction, and it also results in massive enhancement of the magnetic moments of the surface nickel atoms. So this work was done by two students, Niharika and Gaurav, and also I had some useful discussion with an experimental colleague of mine, Nirmalya, and I would like to thank ISO Pune for funding, and thank you for your attention.